Okay, we're going to begin topics in Chapter 5 by discussing geometry. In particular, we're going to talk about Euclidean geometry. And Euclidean geometry is named for a fellow named Euclid. Here's an old artist impression of him. But Euclid was a Ptolemaic Greek. Lived around the 4th century BC. Ptolemaic means that he was one of the Greeks that ended up in Alexandria, Egypt, after Alexander the Great conquered Egypt. Alexander the Great was a Macedonian, but he conquered for the Greeks. And anyways, he often is known as the father of geometry, and they put down a lot of ideas. And Euclidean geometry is really geometry on a flat world, essentially. And that's not really our real world. The Earth, for example, is in the large scale non-Euclidean, but the stuff that they discussed was geometry on an infinitely flat surface. It's like a sheet of paper that is as big as you can imagine. So on this flat sheet, you can have a point. So just a single point represents an infinitely tiny dot, but of course it's bigger than that for resolution purposes so we can see it. But we have a point. Maybe we'll label it, call it point A, and then maybe we'll have another point over here. We'll call it point B. I can attach these 2 points with what we call a segment. So we have here a line, segment, and we can classify this sometimes as line segment AB. If we're going to talk about it, put a little line over the top. When we're talking Euclidean geometry, that usually represents line segments AB. Okay, lines can stretch to infinity, at least in our imagination. So if we start with a point, maybe A, I can draw a line from A and make it extend to, in one direction, any direction actually, and it can go on for infinity in that direction. And maybe I'll pick a point, an intermediate point someplace on this line past point A, so that we could label this and call this line AB, designate it with a little arrow. Lines can also extend in 2 directions infinitely. Here I've got a line I'll label CD, and CD extends in both directions infinitely. Sometimes we call a line that extends only in one direction infinitely a ray. So sometimes we call these a ray. These 2 ideas here represent the first 2 of Euclid's postulates. First one is a straight line segment can be drawn between any 2 points, like we did. And any straight line segment can be extended indefinitely in a straight line. A third postulate states, given any straight line segment, a circle can be drawn having the same segment as radius. So the length of this line segment will be the radius, and one endpoint as center. So let's try this. Now, it should be noted that shapes in Euclidean geometry can be drawn using 2 instruments. One is a straight edge, and for this we'll use a ruler. So this is the compass on the right, and of course on the left is a ruler. And again, any Euclidean object can be drawn with a compass and a ruler. Of course, you need a pencil or a writing instrument to do this. So our third postulate here says, given any straight line segment, a circle can be drawn having the segment as radius and one endpoint as the center. So let's do that. Okay, so let's draw a circle. Here I'll start with a piece of paper, put my straight edge down, and then draw a line segment. Okay, then I'll take a compass and start tracing the red line around. And there you have a circle. Okay, let's talk about congruent objects. Two objects are congruent if they are exactly the same in form and shape, and you could place one on top of the other. For example, suppose I have this triangle here. Now suppose I draw another triangle over here, a red one. These two triangles are congruent if and only if I can place one exactly on top of the other, and the angles are the same, and the line segments are the same, and everything's the same. So if let's say I rotate this thing like so, and then I move it on top of the other triangle, you can see that it overlaps completely. It's congruent. Line segments work the same way. Congruent line segments work the same way. And this brings us to Euclid's fourth postulate, which states all right angles are congruent. What's a right angle? A right angle is an angle that is 90 degrees, like this triangle angle here. Often we represent that with just a little square in the angle, represents it as 90 degrees. So this is just a necessary comment to use to build other more complicated geometrical mathematical ideas. So all right angles are congruent. That means if you have one 90-degree angle, it's going to be exactly the same as another 90-degree angle. And this brings us to Euclid's fifth postulate, which states if two lines are drawn which intersect a third in such a way that the sum of the inner angles of one side is less than two right angles, then the two lines inevitably must intersect. So that's just a long way. That's just a long way of saying if you draw a line and you draw another line, if this line is angled in any way other than completely horizontal with that line, it eventually will intersect that line if you go out far enough. So another way of looking at this is if you have two lines, then a third line drawn that intersects these two lines, then this must be 90 degrees and this must be 90 degrees for these two red lines to be parallel. Or these angles, these two angles, this angle here and this angle here must be congruent. And that's all that really says. And here are Euclid's 5 postulates, all pasted together in a link to where I got this information. So I spoke earlier that the Euclidean shapes can all be drawn with protractors, well, compasses and straight edges actually. And this was kind of key to the Euclidean mathematics. It was kind of based in physical reality, unlike a lot of mathematics today, which are based in equations, and those equations lead to other equations. There is not necessarily physical objects that you can attach to those ideas. But Euclid, his geometry was all based in stuff that you could build physically with the mathematics. So let's try a square. So I'll begin again with a line segment. I draw with my straight edge. Okay, so if I label this point A, this point B, then I take out my compass and I pick a point between A and B, let's call it E, and I pick some distance on my compass just to make things simple. It's going to be, I'm going to use the same distance AB, but you don't have to. And I'm going to extend the line segment to F. Okay, so now I'm going to take my compass and I'm going to stretch it to any size. It doesn't really matter. And I'm going to tack it here to E. Let's see if I can do that. So I'm going to put the left pin on E, and then I'm going to swipe a curve with this side. Okay. Then I'm going to pin it to F. Do the same in the other direction. So like so, a red line I'm going to create. And then if I pull the compass away, you'll see that these two lines cross there. I can then take a line. I can then take a line and start from point B and go through the intersection there, and I will know 100% sure that this angle here is 90 degrees, or a right angle. Now, since I was clever and I made this distance on my compass be equal or congruent to line segment AB, I know then that this point is a vertex of my square. Let's call this C. So now if I were to put my compass on point A, I could inscribe a curve. So I could swipe this orange curve if I put the tip of my compass on A and swipe it. And then I can do the same thing with C. If I put the tip of my compass on C and I swipe it over here, I will get this corner to the rectangle, and you can see of the square, and you can see I've already has the square drawn in here. And then when I erase all those curves, I have a perfect square. Let's call this side D. So perfect square, each of these line segments is 90 degrees from each other, and they're all equal length. And that's where I will stop.